There's no review, it's just the homework. Right?
Well, we're going to talk about that. Okay, so just to be clear, exam 1 is going to be on Tuesday, which is, I don't know what's that date. 18th, right? What month is it? 9, 18, 18. All right. This will cover everything through all material, material through 6.1, which is integration by parts. So that's where we're going to stop. So today I'm not going to present you with anything new. Okay, what we're going to do is, and please do not feel like this is going to happen for every exam. All right, but I'm going to show you some of my old exams, and we're going to go through some of the problems. All right, and part of what we want to do here today is try and address what seems to be a common theme with everyone that I'm meeting with and talking to, and that's knowing what to do with the integral when you see it. Like, do you use U substitution? Do you use integration by parts? When you're doing your homework, you kind of know because you're in the U substitution section, right? So you know what to do. But if you're not given that prompt of what to do, then it can be more challenging. So we'll kind of address that. And you'll kind of get a flavor for what the exams look like. This exam is worth 15% of your grade. And you know, there's no makeup exams, there's no redos, there's no test corrections. It's, you know, I'm trying to prepare you for college, right? Like the college experience. And the college experience as you move on is, you know, there's no more, you know, you have to be ready to show up and perform that day, right? That's just, I took classes in college where we had 2 exams, 50% of your grade. Sit down, midterm, final, that's it. You mess one of those up, it's over, right? So I understand what pressure is like, but you know, we want to try and get used to that a little bit. 15%, the rest of the exams we take are going to be 25%. So that means there's kind of, you can look at that 2 different ways. This exam can't completely devastate your grade, all right? It can't do that because it's only 15%. However, if you do well on it, this is no indication that you can just like, oh, you know, I'm good now, you know, I got a 90 on the first test. I mean, that would be a good sign, but it's in no way enough for you to feel comfortable yet, right? And the reason it's 15% is also because it's not a whole lot of material. Now, it may seem like a whole lot of material to you right now, but it really isn't. Most Cal 2 classes on campus here are not going to be taking a test yet. Most of them are going to wait till they finish all the techniques of integration and then have a first test. And that's much harder because then you have 5 different things that it could be when you look at it instead of 2. So, but this is the way I do it. I'm happy doing it this way, and that's what we're going to do. Okay, any questions before I begin? Yes?
I have a question for, I have a picture. Can I show you?
You have a picture?
Yes.
Do I want to see this?
Pretty sure yes, I'm pretty sure
What is it?
so it's like the, you know how you do the table for
Yes.
for B and DV?
Yes.
For example, sometimes you have sine of 2 pi
Uh-huh.
inside the sine, right?
Mm-hmm.
And then that's on DV. And then when you go back, how do you, don't do the chain rule there. How do you integrate that? You put the 1 over whatever's inside, right?
Uh-huh.
Why? Is that a special rule?
Yeah, didn't we do that? I think we did that. I showed the antiderivative in class. I showed the antiderivative of sine of any linear function. Y'all correct me if I'm not right here, but I'm pretty sure I did this.
Yes, I'm pretty sure you did.
Yeah.
Didn't understand it.
Okay.
You did, yeah.
Well, I
It
didn't.
was a linear one, right?
Yeah, my explanation to it was that if you take the derivative of this, without that, if you take derivative of that, chain rule is going to pop an A out. You're always going to get an A to pop out here, so we have to kill it off. So we do 1 over A here. And then the negative is because derivative cosine is negative sine, so this will make it positive. so that it matches this.
And it's the same thing if it's in the, if it's a product, only a product in there, right? Like 2 pi, it will be 1 over pi.
2 pi x?
1/2, it will be 1/2, right?
2 pi x? Show me your picture.
Just 2 pi.
Sorry about that.
I don't know why I said 2 pi, but I have a picture of this. I saw it twice in like the Humber Proms. So
Cosine, okay, 3 theta,
Yeah,
like
so
that?
you-
Yeah. So if you're doing an integration by parts problem, and down here dv is cosine 3 theta d theta, right? Then when I go up to this one, I'm integrating it, and this right here is linear, okay? It's like 3x, really. So I'm going to have to compensate for that with a 1/3 out front, and then a sine 3 theta.
Exactly,
Yeah,
That's a rule. Yeah.
that's a rule, yes.
It's like a special rule, right?
I don't.
It's not just on doing the chain rule, right?
If this was just theta, then it's just sine theta, right? If this is theta, that's just sine theta. But if it's any linear function in here, then you always have to scale by the coefficient of the variable, which in this case the variable is theta, so you have to scale it by 1/3.
But only big functions, right? If it was something else, then that would be different.
We can generalize this actually to other functions, yep. We could generalize this to any function, in fact. Because any function that would have a linear expression on the inside, if we could integrate it, then we'll always have to scale by that number to get rid of it.
Is there, if it's just like, you got another problem which was sine of t, which is t minus s.
T minus s. T minus s?
T minus s, yes. And constant is t, and it's es. So
Oh, okay, yeah. So the number in front of s is -1. Because it's t minus s, right? So minus s, that's a -1 in front of it. So you have to scale by a -1. You have to do like 1 over -1. Yes?
The later problems, they ask for you to prove the reduction.
That's what we're going to start with today. Yes, I'm glad that you had trouble, or I'm glad that you have questions. Okay, so let me say this. With what I'm about to do with reduction formulas, this would only appear on the test as a bonus question. All right? Not because I think it's any more difficult, but I want you to focus on the things we've been doing, all right? So let's do the notes. Here we go. At the very last one, which we never got a chance to get to, right? This one, it said, find the antiderivative of sine to the nth power of x dx. And we're going to be doing what's called creating a reduction formula. So what do I mean by that? Well, if you own a textbook where the person who had it before you did not tear out the reference pages, then you should know that the formula sheets that you have on Canvas are the first 6 reference pages from the back of your book. Okay, that's what I provide you. But there are actually 10 reference pages. I don't give you all 10, all right? On your test, you can only use the first 6. But if you looked on reference page 9, formula number 73, formula number 73 says this: the antiderivative of sine to the nth power of u du is equal to -1 over n sine to the n minus 1 power of u cosine of u plus n minus 1 over n integral of sine to the n minus 2 of u du. Okay, that's a formula in the back of the book. Now this is called a reduction formula, and let me illustrate how this formula would work, and then we're going to generate this formula. All right, we're going to create this. But let me first show you how it works. Let's say that somebody wanted you to find the antiderivative of sine to the 8th power, and let's just use x dx instead of the u's. So let's say we were asked to do that. Right now, what we have in our toolbox in terms of the techniques of integration, we don't have anything to deal with this. Okay? There's nothing we can do. But if we look in the back of the book, it says if you have sine to any power, then this is the formula for it. All right? So let's just use the formula and see what happens. We would have, what, negative 1 over 8, right? Because the n that we have in the problem, right, this is n for us. This should be negative 1/8 sine to what power? 7th power, that's n minus 1, so 7th power of x, cosine of x, plus, now what's the next thing? 7 over 8, 7/8 integral of sine to the 6th power x dx. That's what the formula would give us, okay? So what we've done is we've taken an integral and we have rewritten it, and now we have a new integral, right? Didn't integration by parts do the same thing? Like we had an integral, we did some transferring derivative, and we got this ultraviolet minus integral voodoo, right? And we had a new integral in it. That's basically what's happening here. But look at this new integral. Is it any better than this one? It's the 6th power, right, instead of 8th. So why don't we use the reduction formula again? Because if I just look at this right here, couldn't I just like, here's my 7/8 plus and then all this crap in front of it, right? Couldn't I just use that formula with the bracket right here and just do it again?
Wouldn't it be the same thing?
Yep, now we have a new n, right?
5 over 6?
Yep, let's see. What would it be? Negative 1 over 6, right? Sine to the 5th x cosine x plus 5/6 integral sine to the 4th x dx, right? Do you all follow? And you see what you would have to do now? And now you would have this one, right? And you could go and do the reduction formula on that one and have that within this one and then do it again and do it again. Yes?
Until you use the rules that you know.
Until you get to something you know, right? Because eventually the next one's going to be sine squared, and then the next one will be sine to the 0, which is just 1. And you can integrate 1. So do you see why they call this a reduction formula? You start with a power that's really high, you use the formula and it reduces the power. And then you do it again and reduce the power, and you reduce, reduce, reduce. So theoretically, this formula can handle any power of sine. You give me sine to the 1,000th power. Yes, I would have to do this like 999 times maybe, but it could be done, yes? Okay. So where does a formula like this come from? And that's what I want to show you. And in the homework, it wants you to come up and verify reduction formulas also. So we are going to create this formula up here, all right? We are going to create that formula. I will never ask you to do sine to the 8th power integral. I will never ask you to do that, all right? Ever. We just want to appreciate how a formula like this is created. Because these formulas, believe it or not, were not created by, well, some superpower or super... I don't want to get... No, I'm getting in trouble. These formulas were like not on the back of some tablet that was given to, you know what I'm saying? Like 10 Commandments type thing. This is, I mean, human beings had to create these formulas, right? It wasn't like we found some scroll that had all these formulas that we'll ever need, right? Okay, here we go. So how do we come up with this formula? Let's start out with the original integral. It's going to be sine to the nth power. I'm going to use x, okay, instead of u. All right, we're trying to do this, right? Now, what I'm about to do is not a very natural step, okay? It's not a very natural step. So let me try and remind you of integration by parts. Integration by parts is this, right? That's our integration by parts. I'm going to use integration by parts on this. Notice that the first two terms right here are u and v, right? And in the integral, this is u and this is dv. So when I'm trying to verify this formula, it's probably a good idea for me to guess that this is my u and this would be my, what? V? Isn't that kind of a good guess? Like if this formula was generated from integration by parts, it's a good chance that this is what they let be the u and this is the thing that they let be the v. Yes? You sure? Okay, so maybe somehow I could get that. But I don't see this here, do I? Because it's supposed to be there, right? So this is the unnatural step. Do you agree that that's the original integral? That's the original problem. So like if this was sine to the 8th power, I could say it's sine to the 7th times sine. Right? So if it's sine to the n, it's sine to the n minus 1 times sine. So we agree that's the same thing? Now, you sure?
Same thing as what? Top.
No, same thing as this. If I say sine to the nth power, then it's the same as saying, well, it's like if I say it's x to the n, that's the same as x to the n minus 1 times x to the first power. You add the exponents, n minus 1 plus 1 would give you n. So these are the same, right? I'm doing the same thing, but I'm using sine to the nth of x is this. Okay? So at this point, I'm going to use integration by parts. And I'm going to choose for you the sine to the n minus 1 of x, and that forces my dv to be the other thing that's here, which would be what? Sine x dx. 6? No. Sine x dx. Y'all with me on that? Can you see now again, when I started this, I had the reduction formula given to me, right? And I'm trying to figure out how my integration by parts table is going to be created. And so what I did was looked at these two first pieces here and realized one of them had to be u. So if that has to be u, I had to rewrite this to make my u show up. And this is the only way I could do it to make it show up. Now, this is v, right? But in the original integral, it's dv. It's a derivative, right? So let's just see what happens here. Let's go up first. What's v have to be? Negative cosine, right? Negative cosine x, right? And am I happy to see that? Look, v is supposed to be this, right? Negative cosine, look, cosine, negative. So maybe there's some hope here. Now, what about the derivative over here? What's the derivative of u? Be careful here. So like if I asked you to take derivative of sine to the 8th power of x, what would that be? 8 sine to the 7th power of x times cosine x, chain rule. Right? That's what the derivative of this would be. But I'm taking derivative of sine to the n minus 1. So what's the derivative of that? N minus 1 comes out. Sine to the n minus 2. The power comes down by 1 of x times cosine x times dx. Any questions on that? All right. So that means this original integral equals ultraviolet minus the integral of voodoo, right? Ultraviolet minus the integral of voodoo. So ultraviolet are these two multiplied together, right? Ultraviolet. So how about I put the negative out front? Then I'll have sine to the n minus 1 of x times cosine x. That's my first piece, right? That looks kind of like this, a little bit, right? I'm missing the 1 over n, aren't I? But I've got the negative, I've got the sine to the n minus 1x, I've got the cosine x. I'm happy, kind of. Minus, I'm going to leave a space here for any constants. And then now it's voodoo, this times this. So what can I pull out? Where are constants here that I can pull out? N minus 1 is a constant, and the negative, right? So when I pull that out, it's going to become a plus, and then I'll have n minus 1 like this. Now what's still in the integral? Sine to what power? N minus 2 of x, and then cosine x, and another cosine x, dx. So cosine squared. Y'all still there? Okay, now this is pretty close, right? Like I didn't have that n down here. I don't have this n down here either, do I? I have sine to the n minus 2 of x, right? That matches, but this I don't have, right? Like this is here, but up here it's not, right? So now comes another tricky part, all right? What I'm going to do now is I'm going to realize that my goal is to not have any cosines there, right? I don't want any cosines to be here. So what's something I could do that maybe I did in pre-cal when I had cosines and I wanted it to be sines instead, especially if I have cosines squared? Trig identity, right? This is actually, using the Pythagorean identity, the same as 1 minus sine squared x, isn't it? That's what that is. So that's sitting here like this. So that means this can be written as negative sine to the n minus 1x cosine x plus n minus 1 integral. And now what I'd like for you to do is take this and distribute it through the parentheses. So what is sine to the n minus 2 of x times 1? Itself. Sine to the n minus 2 of x, right? That's what I get there. Now what about here to here? It's just sine to the n. How are you getting sine to the n? I don't get it. You're taking that exponent and you're adding that exponent. So you're doing n minus 2 plus 2. The 2's cancel, you just get sine to the n, right? So I have here plus or minus? Minus sine to the n of x, right? That's what happens when I distribute. Dx. Yes? All right. That just looks like I made it more complicated, almost, right? But check out this next line. So what I'm going to do is I'm going to rewrite the original problem. Here's the original problem, right? And I'm going to say that that's equal to this, negative sine to the n minus 1 of x cosine x. And then I'm going to say plus n minus 1 integral of sine to the n minus 2 of x dx minus n minus 1 integral of sine to the nx dx. What did I do right there? I have subtraction in here, right? So I can do these individually. So what I did is I created two integrals out of this. And because the n minus 1 was in front of the whole thing, I had to do the n minus 1 in front of this integral, and then minus the n minus 1 in front of this integral. You see it? So that's these two split with an n minus 1 distributed to both. You sure? Why'd I do that? Because I just love to do shit for no reason. Why?
Because they're less what matches.
This integral is the original integral. And it's over here. Remember this happened to us, rabbit out of the hat? I've got the integral I'm looking for, right, is appearing over here. Right? There it is. How many of these do I have? Minus n minus 1 of them, right? So like if this said minus 4, everyone would be happy? If I had minus 4 of these integrals, what would you do now at this point? You would add 4 of them, wouldn't you? Well, I'm not going to add 4. I'm going to add how many? I'm going to add n minus 1 of them to both sides. Okay, so I'm going to, at this point, add n minus 1 integrals of sine to the nx dx. And over here, I'm going to add n minus 1 of the integrals of sine to the nx dx. And how many of them are here, right here, sitting here? How many do I have? I have one of them, right? Okay, so it's gone over here. And how many do I have total now on the left-hand side? N of them, right? If I have n minus 1 of them, so if this said 5, then that would be add 1, I get 6, right? But this is n minus 1, so I'm going to add 1 to that. The 1's cancel, and I just have n of them. So now I have n of these integrals equals negative sine to the n minus 1 of x cosine x plus n minus 1 integrals of sine to the n minus 2 of x dx. Do y'all see it? See what I'm going to do next? And I'm going to be done. What was it in my formula that I was missing here? I was missing that n. Do you see where that n is about to come from? I'm about to divide n on both sides. If I divide this by n, what happens? I just get 1, right? So I divide this by n. And then I have to divide each term by n here. So this is a term, so I divide it by n. So why don't I rewrite this negative 1 as negative 1 over n? And then this n minus 1 that's sitting in front of the integral, why don't we just divide that by n? And the n's cancel, right? And you get the reduction formula right there. That's the original formula, right? There were several unnatural steps in that problem, right? But it's pretty impressive that you can come up with something like that, right? In the homework, do I actually work those out on video? I don't remember. I did those so long ago. I did? Numbers, what, 35 and 37? I did work those out? I did? No. The reduction formula ones. I did not work those on video?
I think you only got to like 29 or 30.
You only got to 30?
30? Okay. So those other problems I didn't do. Yeah. Okay. That's why they're bonus on a test, okay? I mean, so if you're interested in that and you want to try and, now that you've seen it, if you want to try and go for this, you can. But it's bonus, all right? It's more than you need to know for the test. So there, in the back of the book, that was formula number 73. There are 120 formulas in the back of the book for special types of integrals. And in terms of reduction formulas, there's one for sine to the n, cosine to the n, tangent to the n, cotangent to the n, secant to the n, cosecant to the n. And I've seen entire books this thick full of integral formulas. So back before computers and stuff, engineers and stuff would use a reference book to go find that integral they're trying to figure out, right? They'd be like, where is it? Okay, mine looks just like that one, and I'm going to use that formula, right? So that's the way it used to be. Now you just go to Wolfram Alpha, type in the integral. Y'all know Wolfram Alpha? Okay. All right, that's it. Did that help? Okay. Now let's talk about some more integration. So I'd like to take a look at a test from spring 2016. So I gave the class I gave them 10 problems and a bonus. And the bonus was to prove a reduction formula. Now don't sit here and be like, get your phone out, take pictures and be like, this is the test. The idea here is to give you just a feel for how many problems I asked, the types of problems there were, all right? I asked 10 problems. You have 100 minutes. That's about 10 minutes a problem, okay? The first few had to do with derivatives of hyperbolics and things like that, so I'm not even going to get into that. I'm just going to get into the ones that I think are interesting here, specifically this one right here. I think that's an interesting one. Can you all see that okay? So what makes this one interesting is that, well, I don't know. I mean, you tell me. It's what makes it interesting. Is it a basic power rule, or is it U substitution? Is it integration by parts? Integration by parts. I'm hearing a couple of votes for that. How about U sub? U sub. Okay, if it's U sub, you're trying to see something in its derivative, right? That's not trapped. That's kind of a problem here, because you might be thinking x cubed is U. And then the derivative of it is like 3x squared. You have x squared, but the problem is that x squared is trapped in here. So a basic U substitution of x cubed won't work here. So maybe something else. 1 plus x squared. It may not seem like that's going to work here. Let's just go for this. Du would be 2x dx, right? So now you're trying to see, like, do I have something? Yes, I have it. Do I see its derivative? You're looking for, well, the 2 we don't care about, right? Because we can get rid of the 2. But do I see an x dx? I see an x cubed dx, but I don't see an x dx, right? So what we need to do first is rewrite this as x squared over the square root of 1 plus x squared times x dx. So peel one of the x's off the x cubed and move it out to the side. Is that like a legal algebraic move? I mean, x cubed is x squared times x. Yes?
What makes you automatically see that?
This was not my idea. Who said 1 plus x squared? Ask him. I'm not sure why.
No, I understand that, but how do you automatically see that you have to feel something else?
It's not that I see it, it's that I'm trying to force the problem to behave the way I need it to behave if I'm going to use this substitution. If I'm going to use this, then I need x dx somewhere, right? And I'm just saying to myself, well, I've got 3 x's, right? So why not peel one off and hope for the best? I still don't know if this is going to work, right? So that now matches this, right? So I don't want the 2, so I'll just multiply both sides by 1/2. So now I'm kind of like in business here, right? I've got this, I'm all happy about that, right? I've got that there. I've got 1 plus x squared, that's going to be U. I'm so happy about that, but I still have x squared up there. So I've got to somehow turn the x squared into something with U. And I can use anything I want over here. Just take that one. Look, it has x squared right there. So solve it for U. Solve it for x squared. Just move the 1 to the other side. U minus 1 is x squared. Right? It just works this way. Now, I'll tell you right now that if that were x to the 4th, we'd be dead in the water. Okay? We would not be able to do this problem. The problem had to be very carefully chosen and created in a way that this would work. Do you understand? If it was x to the 4th, you could peel off an x, but then you would have x cubed up there, and I don't have anything here with x cubed. It would also work if I did x to the 5th power, because I could peel one off, then it would be x to the 4th, and then I could basically say, take this and square it. But, okay. We good? Can I rewrite the problem now? Okay. So this is going to become integral x squared for us now is U minus 1. And then over the square root of what? U. And then x dx is being replaced with 1/2 du. So the half I'm going to bring out, and here's my du. It looks like it got a little nicer, didn't it? I mean, that looks nicer. How do you handle that integral? Yep, so you go integral, let's see, 1/2, and then how about we rewrite this as u over root u minus 1 over root u du. So I'm just using the idea that I have a single term on the bottom, multiple terms on the top. They're all powers of u, so I'm going to split them apart. So this becomes 1/2 integral, what is u over root u? U to the half. So you're basically taking the power 1 here and the power 1/2, subtracting, and then minus, what's this? U to the negative 1/2, right? Du. And then now you can use your power rule. Shall I take it all the way? Yes, take it all the way? All right, so this equals, now I'm taking the antiderivative. So I have 1/2 sitting in front. The antiderivative of this, I add 1 to the exponent. 1/2 plus 1 is 3/2, right? So out front it's going to be 2/3. U to the 3/2. And then minus, and then I add 1 to this, and I get positive 1/2. So out front it'll be 2. U to the positive 1/2, and then plus c. Distribute the 1/2 through. So let me move up here. If I distribute 1/2 through, I'm going to get what? 1/3? 1/3 u to the 3/2, right? But what was u? Let's go ahead and plug u back in. What was u? 1 plus x squared. All that to the 3/2. And then minus, when we distribute the 1/2 here, it kills off the 2. And we just have, you could put square root, doesn't matter. You could leave it as 1/2, or you could write it as square root. There it is. If we take the derivative of this and simplify it and clean it up, we should get that. So that's a problem where substitution works, but you got to go with it, you know? And you got to kind of massage the problem a little bit to make it look the way you need it to look, right? Okay, let's see if there's anything else that's interesting here. Could I do that with integration by parts? Maybe. Let's look at it. Let's look at it, okay? So what would you, if you wanted to do integration by parts here, what you'd probably hopefully be saying to yourself is, you know, I've got to choose one of these to be my u, and the other one is going to be my dv, right? So I'm going to differentiate one of these and integrate the other one. Yes? In the table, that's what I'll have to do. I don't mind differentiating x cubed. 3x squared, I'm done. But I kind of do mind integrating this, right? Would you want to integrate that? I mean, do we have a formula for 1 over 1 plus x squared? Look on your formula sheets. We have one for 1 over the square root of 1 minus x squared, don't we? That's arc sine. But what about plus? We actually don't have one. Okay? We haven't done it. We can handle it. We can handle this integral, just not yet. Like that by itself, we can do, just not yet. All right? We don't have enough tools in our toolbox yet. So right now, integrating this is not easy. Right? So then maybe the other way. I could let this be u and then that be dv. So I'm going to do the antiderivative of this, which is 1/4 x to the 4th, and then I'm going to differentiate this. But if I differentiate that, I mean, that's really 1 plus x squared to the negative 1/2. So if I ask you to differentiate that, you have a whole lot of crap happening here, aren't you? Like negative 1/2 is going to come out. It's going to become negative 3/2. Then you're going to have times 2x inside. You see how that's going to look pretty complicated? So I think if I look at this originally, I think, integration by parts, I kind of run through both ways and I kind of convince myself that it's a no-go. And that U-sub should probably be employed somehow. Good question. All right, let's look at another one. By the way, that problem is straight out of the book. And it was on my test. And I did it on video. Right? I had to have done that on video if it's... Let's look at this next one. I don't think I'm going to work through it, but let's just talk about, again, recognizing what to do here. So what do you do here?
Yeah, you do a reduction.
What do you mean reduction? We don't have any reduction formulas. I haven't given you any reduction formulas. Yeah, the one we have had sign in it, right? And that, by the way, like those are off the table. I would never ask you a problem that would require a reduction formula. So one thing you could do is you could take 4 minus x and multiply it times itself 10 times. Right? No, you don't want to do that, right? Integration by parts. Let's run through that. If I told you have to use integration by parts on this problem, then what would you choose for your u? Probably the x, right? And then what would you choose for your dv? Everything else, right? But then you have to integrate this, don't you? And that doesn't look very fun, right? And if you integrate this, it's going to be the 11th power of this once you integrate, right? I mean, it's got to, because if it's 10th power, then when you integrate, you're going to have at the least 11th power. And then over here, you're going to have, if you differentiate, you have 1, right? So I don't want to do this, and even if I did it, my diagonal is going to have something with the 11th power, which still looks bad, because I can't even do this one with the 10th power, right? So maybe you think integration by parts the other way. So you do like 4 minus x to the 10th here, and then you do x here. So we could differentiate that, right? 10 would pop out, this to the 9th power. Then we integrate that up, we're going to get 1/2 x squared. We put those two together, it's still bad, right? Because this has x squared in it, and this has this to the 9th power. That's just as bad as this to the 10th and that to the 1st. In the new integral, it's going to be this squared and that to the 9th. Does it help? Do you see what I'm saying? So I'm starting to rule out integration by parts here. I did one like this in class. U sub. What's the substitution? 4 minus x. This was an example of a U substitution where it doesn't look like that's going to help, but it actually does. It works. What's the derivative over here? What's du? -1 dx, right? Do I have a -1 dx? Well, I have dx, don't I? But I don't have the -1. So why don't we just make that negative du and make that +1? So at this point right now, I'm going to be able to rewrite this with u, correct? That's going to be u. I'm going to be able to rewrite 1 dx right here. I'll be able to rewrite that, yes? The only issue we have is to resolve that x out front. And we do the same thing we did before. We take that right there and we solve for x. So what would x be here if I solve that for x? 4 minus u or -u plus 4, however you want to do it. 4 minus u, is that okay? And so you go back up here and we rewrite the integral now. What's x? 4 minus u, put it in parentheses. What is 4 minus x to the 10th? U to the 10th. And then dx is actually negative du, so I put the negative on the outside. And why is that better than what we had before? Now you can distribute. You can distribute the u to the 10th through. Here you cannot push the x in. because order of operations says we have to raise this to the 10th power before we do any multiplications. Here, the 10th power is on the u, so we can pass it through. So this becomes integral u to the 11th minus 4u to the 10th du. What did I do there? I distributed the u to the 10th through, right? And then I passed the negative back in. Is that illegal for me to do that? Yeah. And I can do each of those individually with power rule, can't I? So this will be 1/12 u to the 12th minus 4/11ths u to the 11th plus c. And the last step would be to replace u with 4 minus x. So the problem I showed you before this, I told you it was in the book, right? It was actually number 34 in the book on 5.5 on substitution. This problem I do not believe is in the book exactly, but there's got to be one close to it. Well, I did this in class, though. Do y'all remember I did one that I put like power was like, I don't know, 20 or 200 or something like that? Okay, let's look at something else. We're halfway through class here, so let's see here. Look at this one here, 6. So what are you thinking for this one? U-sub? Okay, if you're going to do U-sub, anyone want to venture out on a limb here and tell me what they want their U-sub to be? Okay, so I'm hearing two things. I'm hearing natural log x, and then the other one I heard was what? Root x? Okay, let's put these up against each other. Natural log of x versus root x. Which of these is going to work? All right, what's the derivative of natural log of x? 1 over x dx, right? Okay, do you see a 1 over x dx? I see a 1 over root x dx, right? But I don't see a 1 over x. So you might say to yourself, well, just take the square root on both sides, right? Maybe that's what you're thinking. Can't do that, because if you take the square root on this side, it's going to root the 1, the x, and the dx. And in this integral, you don't have a root around the dx. The root's only on the x. So then you might say, okay, I'm going to go up here and solve for x. But do you see what would happen? Like if I come up here and solve this for x, the only thing I could do is like e on both sides. That would kill off the natural log. And then I could take the square root on both sides. But do you really want to replace that with that? I don't think you want to. That would make the problem a lot more complicated. Would you agree? So far, it looks like root x might be the winner here. Do you all agree that so far it looks that way? Okay, so what about root x? The derivative of that is what? 1 over 2 root x dx. And do you see 1 over 2 root x dx? Well, look. Aren't I saying that this is u? Right? So this is 1 over u, right? That's 1 over u. The only thing I have left to play with is dx and natural log x, right? But I've got this here that has another root in it, right? It's like I need another root there somewhere. Do y'all see that? Which means what? That this fails too, so no one won. They both lost. U substitution is not going to work. Do y'all see why U substitution is not going to work? Okay. For this one? Okay. Somebody said we're going to let U be root x, right? So this right here is going to be U. So we're hoping in the new integral we're going to have 1 over U there, right? That's going to be 1 over U. Now, when I take the derivative over here, du is 1 over 2 root x dx. But I still have to somehow get this and this switched over to U somehow, right? So what are you going to replace natural log of x with? You have no information about natural log of x here, right? So how are you ever going to get rid of natural log of x if it's not over here? Got it? Okay, good. All right, well, if those two failed, then there's really only one other option. Yep, integration by parts. Okay, so if we use integration by parts, let's consider the two possibilities here. Right? We have to choose one to be u and the other one dv. Time is always an issue on this test. For every student, time is always an issue. And part of what you're being tested on is how effective you are and how efficient you are. You know, you see the problem, you recognize it. Like if you have to go through each of those u substitutions and then go to integration by parts and have to check each way, that's just going to slow you down, right? So part of this is, do you look at that and realize right away, I can't use u substitution, right? The only way I'm going to be able to know not u substitution is to real quickly in my head go, if u is natural log of x, the derivative of it is 1 over x, and I don't have that. If u is root x, the derivative of that is 1 over 2 root x, and I don't have that, I've got a natural log. U subs out. Right? If you can do that mentally quickly, then that's good. If you have to write it all out, finishing the test is going to be tough. Yes? Okay.
The only way to improve it is by practicing it?
Yeah, I mean, just the way I did it right now. I mean, when I look at this problem, right, when I look at this, I rule out u substitution in about the first 10 seconds. I look at it, I say, okay, if you use natural log x, 1 over x, I don't see that there. Now, you know, if this was maybe x squared down here, I might be able to do something, but it's root x, so, I mean, yes, there's experience, takes time to get comfortable with this. All right, integration by parts. dv. So you have to choose one to be u. So when you get here, you're thinking one of these gets differentiated, the other one gets integrated. So you have to choose which one. So again, we run through this mentally quickly. Would I want to differentiate this? Sure, I could get 1 over x. Would I want to integrate this, which by the way is x to the negative 1/2? Could you integrate that? Yes. And you would get like x to the positive 1/2 with some constants and stuff. So if I differentiate this, I get 1 over x. If I integrate this, I get x to a power. In the formula, that diagonal is what I'm going to integrate, right? So, I don't know. What I'm writing on the board is what I'm actually mentally visualizing. dv was the 1 over root x dx. So I'm visualizing this as I look at it. I'm saying, okay, I've got a natural log over here that's going to go down to 1 over x, and then this one over here is going to go up to a power of x. And when I put those together, 1 over x times a power of x is just going to be a power of x. And that's something I'm comfortable integrating. Yes? As opposed to the other way, which would be putting this to be here, which again, I don't mind differentiating that. This is x to the negative 1/2, right? I'm comfortable differentiating that. That's power rule cal 1. But here would be what? Natural log x dx. How do you integrate natural log of x? We haven't done that, right? I mean, like, we have not integrated natural log x. But Sophia, I promised you I would do this today. We're going to integrate that. We'll do it after this. Okay, so right now we don't have a clean way up from here, right? Which really makes it look like that's the way to go, yes? Do you want me to finish this? Or do you want to see another problem where we go through the process of figuring out what to do? New problem? Okay. This is the one that we would do, right here. Let's do natural log. I said we'd do that, right? I'm going to put a star next to this one. And the reason I'm putting a star next to this one is because I do not allow you to do anything with your formula sheets. Like, you can't go take the formula sheets that you print off Canvas. You can't, like, go write a bunch of your favorite things on there, okay? You can't draw a unit circle and bring it in. You're not allowed to touch those formula sheets, with the exception of anything I tell you can put on there, and this you can put on there, all right? You're allowed to put this on here, on your sheet. That way, if we ever have to integrate natural log again, we'll have a formula for it, all right? I mean, shoot, we know how to differentiate natural log, right? We may as well know how to integrate it. We know how to integrate and differentiate e to the x, which is the inverse of this function, so we may as well know both ways on this one. All right, well, we only have one option in terms of the method. What's the only method that you think is going to work here? Integration by parts. And when we do integration by parts, we only have one choice for you. Natural log of x. And that forces dv to be what? 1 dx. Right? That's the only route we have. And differentiating natural log x just gives us 1 over x. And integrating 1 dx gives us x. And look at the diagonal. 1 over x times x is 1, right? So this is going to be ultraviolet, this times this. I'm going to put the x in front of the natural log x. And then minus integral. Do I need to actually write down 1 over x times x? I forgot dx here, everyone. dx. Do I need to write down x times 1 over x, or can I just write 1? I'm going to write 1. 1 dx. And what's the antiderivative of 1? X. So x ln x minus x plus c is the antiderivative of natural log of x. Do you believe that that's the derivative? I mean, the antiderivative? Well, we could check it, right? Product rule. Check it out. It's super clean and easy to do this. It's actually kind of cool looking. Product there, right? Derivative of that would be 1 times this plus derivative of natural log of x times that, x. Okay, so we're done with product rule. Minus derivative of this, 1. Okay, but what's 1 over x times x? 1. So 1 minus 1 there is 0. And you just get natural log x. Yes?
Just a side question.
Yes?
The question from earlier? Is
Yes.
the right answer right? My doo-doo's on the top right.
You're missing a constant when you integrated on your table there. The first table, when you integrated 1 over root x, that was x in negative 1/2. When you go up there, you're going to get 2x to the positive 1/2, I believe. I don't think you integrated it when you went. I think you just kept it the same. But it's still, like, you got an answer, but that's off. Yeah.
It was a dumb answer.
Yeah. Well, that's not a dumb answer. It's a correct answer based upon your mistake. So you used the rest of the table correctly. Like, you used everything right, but that top right corner was wrong. All right. What about this one?